Good morning.
Good morning, sir.
Yeah, so in the last class, I was discussing about image restoration. Uh, so can any one of you just define what do we mean by image restoration? Can somebody voluntarily do that?
Sir, image restoration used to reconstruct an image from part which is already degraded.
Okay, good. So yes, the definition is almost correct, but there is a little more to be added to your definition. So what is that? It is reconstructing or recovering an image that has been degraded, correct? But we need to know something else. Okay, I'll just share my screen. Okay, the slides visible.
Yes, sir.
Okay, yeah. So as somebody said, image restoration is basically to reconstruct or recover an image which has been degraded. But what is important is we should have some a priori knowledge of the degradation phenomenon. So that is very important. I should know how the image was captured. For example, it could be uh, maybe a moving vehicle captured by a still camera, or the opposite. The camera is on a moving vehicle and you have captured, or the camera is not focused properly. That means the lens settings is not proper, or maybe the image is captured when there is probably atmospheric variations. So I should know these degradation phenomena that has happened so that it is easy for me to model the process. So there are two steps, as I already explained: modeling the degradation process and then you apply the inverse of it. In fact, we also made a comparison between enhancement and restoration. Um, Enhancement is subjective, whereas restoration is objective. That means we have a specific objective of removing the degradation, whereas in enhancement it is subjective. We want the resulting or output image to look better than the input image, maybe in terms of the contrast or in terms of the edges or maybe in terms of the visualization. Okay, so we looked into the model. There is an input which is a degraded image, there is an output which is the restored or the cleaned image. And what we should know is the noise that would have corrupted the image, and we should have a model for the degradation. And it would be good if you know some information about the original image. Okay, there are two approaches, as I mentioned in the last class: spatial domain and transform domain. So this is a very important slide. This is a model for degradation followed by restoration. This is a complete model, and we have made some assumptions here. The assumptions, I think all of you know. The first assumption is uh, the system, or which is your camera actually. This is a linear and shift invariant system. Okay, so last class somebody defined what is an LTI system. For a two-dimensional signal, we use the term linear and shift invariant because there is no time concept in an image. Of course, time concept can come if it is a video. If it is a still frame, then we don't talk in terms of the time, we don't talk in terms of the space. So that means there is a shift in the image So we call it as linear shift invariant system. So if I make the system to be linear and shift invariant, then obviously you know that the output of an LSI system is the input convolved with the impulse response of the system. And I also told you in the last class, usually for a two-dimensional system, we don't call it as impulse response, even though it is true. We actually use a different nomenclature called point spread function. Okay, so last class I didn't explain what do we mean by point spread function. So let us spend some time on this. Now, uh, okay, can somebody tell me what do you mean by impulse response of a system? What is impulse response of a system? Either you can chat or you can just answer unmuting. But I want an answer. What is impulse response of a system? In fact, the answer is there in the question itself. It's only that you have to just modify the sentence. Anybody? Prajwal BC?
Yes, sir.
Yeah. Why don't you try? What is impulse response of a system?
Sir, it characterizes the system, sir.
That's okay, but what do you mean by impulse? For example, if you want to find impulse response of a system, what has to be done?
A convolution has to be done, sir.
No. Convolution, when you know the impulse response, you can do it to get the output for a given input. But to get the impulse response of a system, what should I do? There is answer in the question itself. Impulse response. What is the meaning of that? What should be the input to the system so that the output is impulse response?
Should be an impulse.
Correct. That's all. Correct. So when I apply an impulse at the input, whatever response I get at the output of the system, we call it as the impulse response of the system. Okay. So now the question continues to somebody else. An impulse, all of you know that it exists at n equal to 0 or t equal to 0, depending on whether it is continuous or discrete. Now, what do you think would be an impulse in two dimension? Anybody? In two dimension, how does an impulse look? In one dimension, all of you know, it is just uh, non-zero at n equal to 0 or t equal to 0, whereas all other values it is 0. What is an impulse in two dimension? Shivam, can you try? What is an impulse in two dimension? Shivam, are you there? Not there?
Yes, sir. Yes, sir. I'm there.
Okay, yeah. So what is an impulse in two dimension? How does it look as an image? Any guess?
So like a fire filter, I can say, in two
No, no,
dimensions.
no, 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 no. Don't complicate the question. Okay, let me just go to a simple simulation. What I have done here is, if you observe the code, I have taken an image of size at 512 cross 512 and all the values as zeros. Exactly at the middle, 256. Okay, I have made the value equal to 255. That means the central pixel value is 255 and all other values are 0. Okay, that is how an impulse looks like, right? That means you should have all the values 0 and only at in fact, why I have centered it, because you want to look at it as a an image, you know why centering is done. So don't think that this is okay, non-zero. According to me, this our origin is 0. So at the origin, I am making it as 255 and all other values as 0. And let us just show it as an image. So I'll just run this. You may not be seeing anything because you know all the values are 0, only one pixel is non-zero. I will just zoom it. Okay, so do you see something now?
Yes, sir.
Okay, so
Yes.
you see a white dot at the center and all other values are 0. Okay, so this is actually a two-dimensional impulse. That means at the origin the value is 255 or the intensity is maximum. At all other values the maximum the intensity is 0. So that is exactly a two-dimensional impulse. On a one-dimensional impulse, at the origin you will have the maximum value and all other values are 0. In two dimension, at the origin you have the maximum value which is white, okay, and all other values are 0. Now if you look at this as a light source, I can call this as a point source. Okay, a point source means only at one specific point you have the intensity maximum, all other values are 0. Okay, so this is called a point source. Now suppose if I apply such an input to a system. Okay, so I'll apply such an input to a system. Depending on the degradation or the blur that happens, the output will actually look different. Let me just run the simulation further and then demonstrate it. So what I'm doing is I'm just assuming that my system has got a box type of blurring. We have seen this type of kernel in the last class, in the last module. So let me just run this and show you the simulation. Okay, now observe, this is of course after zooming. So we will just go back to the original. So I have a dot here, and because I have blurred it, you can see that the dot has spread. Do you see this? This is a spread of the dot that we showed in the previous. Okay, so this was the dot, which is a point source of light, and when it passes through a system which it introduces some blur, this point source of light is actually spread. So you can observe that spread here. Okay, so applying an impulse to a system, let us go back to the slides now. Applying the impulse to a system, an impulse to a system means that a point source is being in fact captured by a camera. That is the meaning. A point source of light here, that is an impulse, and what you saw at the output is this point source of light. Because of the blurring that is happening due to the camera, it is spread. That is the reason we call impulse response of a system in two dimension as the point spread function. In short, it is PSF. Okay, is the point clear why we call it as point spread function? A point source of light applied to a system, the output response is a spread of this point source of light because of the blurring. That is why I get we call this as point spread function. Okay, PSF. Is the point clear? Why it is called point spread function? Can somebody respond? Yes, I think Rakshita is saying yes. Okay. Okay, so this is the reason why it is called point spread function. So point spread function is actually the impulse response of a two-dimensional system. That's what you can say. Now, suppose a point source of light, if it has to appear as a point source of light here, then can somebody tell me what should be the PSF or what should be the impulse response? I'll repeat the question. A point source of light should continue to be a point source of light at the output. That means there should not be that spread. Can anybody tell me what should be the impulse response of the system, or what should be the point split function of the system? This is a very important, in fact, question on degradation functions. I repeat, or I'll put a question in the different way. I apply an impulse at the input. When will I expect the output also as an impulse? An impulse should continue as an impulse at the output. So what should be the impulse response for such a system? Anybody? I'll be very happy if this question is answered. I'm waiting for some answer through chat, or maybe unmute and speak. Impulse, what should be the impulse response of a system which gives me an impulse at the output when the input is impulse? Nobody wants to comment? Okay, I'll elaborate the question probably. With one dimension, let us try to understand it. I'll use OneNote for this. Okay, so okay, so let us just put the question like this. Suppose if I have a system, let it be one dimension only. If input is say delta of n, impulse response of the system is h of n, output is y of n. At least can somebody tell me how do I write y of n? Okay, let me just put it like this. Okay, so what is the output? Input is delta of n, impulse response is h of n, the system is LTI. What is the output? What is the output? Sushma
Sir,
Shankar.
impulse of
Sushma Shankar. Sushma Shankar, unmute and speak. If you cannot speak, you can chat.
The S of X convolution H of
Correct. Input x of n is delta of n here, so it is delta of n convolved with h of n. Correct. Output of an LTI system is convolution of input with impulse response. Okay. Now, if I want y of n equal to delta of n, what should be the impulse response? This is a question I have asked. Delta of n, when convolved with what, you will get back delta of n? Anybody? Delta of n, when convolved with what, you will get back delta of n? No idea? Yeah, I think you are about to appear for interviews. These are very basics of signal processing. When I convolve impulse with what, I'll get back the impulse. This is one of the property of impulse response. Impulse. I don't know whether x of n convolved with delta of n. What will I get? Can somebody tell me? X of n convolved with delta of n. What will you get?
Sir, X of n.
Yes, this is exactly what I am asking. When I want this to be same as output should be same as my input x of n, what should be convolving delta of n? So what should be delta h of n? What is h of n? H of n should be delta of n, correct? If impulse
Yes, sir.
response of a system is an impulse itself, then output will be impulse. That means a point source of light here I will get a point source of light here. So what is the meaning of impulse response is an impulse itself? It doesn't do any variation to the input. Whatever input I apply, I'll get back the same thing. That means when I take a camera and capture whatever is there in the scene, without altering it, I should get back the same scene here. That means it should not blur or it should not degrade the image. That is the meaning. Okay, so let us go back. Fine. So if the impulse response of a system is an impulse itself, that means it doesn't alter anything, so the output will be same as the input. Okay, so that means if the camera doesn't introduce any degradation, the output here will be same as input. Why I am telling you this? Because this is a model now. Now suppose if h of x comma y is an impulse, which is delta of x comma y. Just now we saw that delta convolved with f, I'll get back f. So my output will be g equal to f plus eta. Okay, that means this will not spoil the image. Yeah, I'll get back as it is. Noise gets added and I'll get, so the output will be only noisy. It won't have any blur. Actually, there are two degradations, blur and noise. If I assume that the camera doesn't introduce any blur, that means the impulse response of the camera or the impulse response of the system is an impulse itself, which is delta of x comma y. This convolution will be equal to f. So I'll get g equal to f plus eta. Therefore, this would be noise only filtering. Remember when I was just telling you in the beginning, I mentioned that restoration in the presence of noise only. So the assumption that we make there is, we will assume that degradation won't be there. That means the blurring won't be there. Degradation is only due to noise. So there are two degradation parameters, blur and noise. In one case, we assume there is no blur and then try to modify this equation and solve for it. Okay, fine. Now, if I take this to the frequency domain, all of you know that I'm using u and v for the frequency. So capital G is for the Fourier spectrum. So G of u comma v is h of u comma v, f of u comma v. And what is happening here? Can somebody tell me? Here there was convolution here. When I took Fourier transform, something else has happened. What is it?
Multiplication.
Yes. So you all know that convolution in time domain or spatial domain is multiplication in the transform domain or frequency domain. So capital H is the frequency domain representation of the degradation, that is the blur phenomena. Capital F is the Fourier spectrum of the image, plus capital N of U is the Fourier spectrum of the noise. Okay, so as an equation this looks very good. Okay, as I said, G, H, F, N, all of them are in frequency domain. Okay, but I don't think this is possible. All of you know Fourier transform is for deterministic signals. I cannot do Fourier transform of a random signal. So, but you know that noise is random. So as an equation, this is okay. If you look at this as a mathematical equation, it's okay. But there cannot be Fourier spectrum of noise because noise is a random phenomena. It is not a deterministic signal. It is a random signal. Okay. Then we have made huge assumptions here. I call huge assumptions because many of them, in fact, realistic. They are not realistic. But if you want to solve this complicated problem, okay, and get back a restored image, these assumptions are necessary. The first thing we already saw that the blur function is, that means your system is linear and shift invariant. That is why we could write convolution. The second assumption we did is noise is additive. That is why there is a plus sign here. Uh, there are different types of noise actually. Uh, you have actually multiplicative type of noise also, but that is beyond the scope of this particular course. In fact, most of the researchers, they have in fact deviated from additive assumption for noise, and they have done in fact the uh, development of algorithm. But in this case we are assuming that noise is additive. This is a simplistic assumption, but we need to go with this because we need to solve this complicated problem. Another third thing is your noise usually is assumed to be Gaussian. Okay, we will take different noise models a little later. So we make Gaussian assumption for noise. That means the those who did, of course, all of you know the bell-shaped curve for Gaussian distribution. But those who did random process, you have learned more about this Gaussian distribution. So we make an assumption that noise is always a Gaussian noise, okay? But there can be different types of noise, particularly in medical image processing, we get many other types of noise, okay? And another assumption is we assume that noise is zero mean. Now there is an advantage in making this assumption. Now all of you know that Gaussian distribution expects two parameters. What are the two parameters? Can somebody tell me? You can define a normal distribution or Gaussian distribution by two parameters. What are those two? If you remember the equation, I think you know. Yeah, mean and variance. Purnima says mean and variance. Correct. Correct. So there are two parameters, mean and variance. So I am assuming that mean is zero. And this is realistic because you know on an average, see noise gets added, so the value changes. So if you just keep on averaging it, the noise will be zero. That means if I capture the image several times, on an average the mean value will be zero. Okay, so I have knocked off one parameter. The only parameter left with is variance. So now assumption, sorry, making a noise to be Gaussian and zero mean has brought me to a stage where when I want to estimate noise, I have to estimate only only one parameter, that is the variance of the noise. So if I just find the variance of the noise, which means that I know the complete details about the noise. Another assumption we make in further, in fact, uh, performing this restoration is we assume that noise is independent. Okay, those of you who have done course on random processes know what do you mean by independent random variables. I'll not go in detail with this. Please just refer to some literature. What do you mean by independent random variables? Because here noise is a random phenomena In fact, image also is considered to be random, because in image also you have done quantization. Because of this quantization, definitely there would be randomness in the image. So noise is assumed to be independent of the in fact the image. So we assume noise as independent. Not only that, we assume that it is identically distributed. What do we mean by that? If I take an image, every pixel could be treated as a random variable. So the noise will corrupt every pixel, can corrupt every pixel. What we assume is every noise random variable has got the same distribution. That means any pixel x comma y and any pixel to the neighboring pixel of this x comma y, both of them will have the same distribution. That means if I assume Gaussian distribution for the noise, all the pixels are in fact corrupted by Gaussian pixel distribution only. Suppose if you don't have this assumption, that means one pixel is corrupted by Gaussian type of distribution, other pixel is corrupted by some other distribution, it is very difficult to remove such noise. So fourth assumption is noise is independent and identically distributed. In short, this is called IID, independent and identically distributed. I think those of you did random processes, we discussed something about this IID random variables in detail. Then while doing random process, we also defined a parameter called correlation, and uh, here we make an assumption that the noise is uncorrelated with respect to image. Okay, again, please refer to the literature. What do you mean by uncorrelated random variables? So noise is uncorrelated, and a big thing is we assume that H and N are known. That means I know the blur or the degradation, I know the noise. So that is why I said huge assumptions, because you cannot expect all this to happen. This is an idealistic scenario, but unless and until I make such assumptions, I cannot move, because this is a very complicated problem. Okay, because lot of unknowns here, a lot of okay. First of all, if I don't have this convolution, then I don't think I can have this simple equation like this. So with this huge assumptions, if we move on, mathematically restoration is simple. What do I mean by that? If I give this to a mathematic expert and I say I see this is the degraded image, this is the blur function, this is the noise, so this is your original image, f of x comma y is original. So by somehow if I find f of uv, then I can do inverse Fourier transform, I can find f of x comma y. So simple is the problem. So it looks like simple. So what do I do? I'll just keep this here. Mathematician says take this to the other side. So it is g minus n and divide by h, I'll get f. Okay. So in frequency domain, it looks so simple. But all of you know, there are so many unknowns here. Okay. First of all, I don't know noise. First of all, you cannot represent the noise Fourier transform or Fourier representation for noise, because noise is random. Next thing is you may not know the blur. Okay, even if you estimate, the estimate may not be very good. Okay, so it is not so simple. So that is the reason why restoration, they say it's a difficult process, because there are so many parameters here and we make so many assumptions and we move on. Okay, now yeah, so let us just try to see some noise models. All of you know that whenever I am acquiring an image, I do digitization, and you know that quantization introduces noise. Okay, we call this as quantization error or quantization noise. I think during the last discussion in the random processes, we had taken actually a specific problem and evaluated signal to noise ratio. I hope those who attended the course remember it. So noise can be there because of digitization itself. Noise can be there because of the, in fact, the problem with your camera itself. That means the sensor noise could be there. And when you transmit a noise from one place to the other place through a channel, because of the noise that gets added during the transmission, there could be noise. And we also know that the sensors, because after all sensors are these electronic devices, they are the transducers which convert one form of energy to other form of energy. So they are affected by environmental conditions. Okay, for example, light levels that is falling, the temperature of the sensor, all these devices are depending on temperature. So they can introduce some noise. Interference in the channel can add noise, we know that. If it is wireless network, definitely the atmospheric variations like lightning and any turbulence in atmosphere can add noise. Okay, so these are the various reasons for noise: acquisition or digitization, transmission. Due to environmental conditions, the sensors can introduce noise. There could be channel interference. There could be lightning or atmosphere. So either I pass it through a wired network or wireless network, I am sure that noise is going to add to the image. Now what I have written here in red color is a very important thing. In fact, I have taken it from Gonzalez and Woods. This was in the second edition I have taken it. You can refer to that. What he says is the complexities of dealing with spatially dependent and correlated noise are beyond the scope of our discussion. Okay, because if it is spatially dependent, that means at pixel at 100 comma 100 is corrupted by one type of noise, pixel at 100 comma 200 is corrupted by another type of noise, then it is very difficult to remove that. And if the noise is correlated with the gray level value, again this is a difficult thing. So we are not making the, we are making the assumption that they are spatially independent and uncorrelated. That is what we have done here. Fine. So as I already told you, one of these specific example for noise model in image processing, which in fact is true even in other one-dimensional processing also, is a Gaussian type of noise. So I don't think we need to really spend much time on this. All of you know the equation. So here Z is the variable or the random variable. The probability distribution is expressed by this equation, and you know that mu is the mean and sigma square is the variance. And you also know that area under the PDF has to be equal to 1. Okay, this is a condition for a specific function to be a probability density function. Those of you who have done mathematics on a random variable theory know that. So this is an expression for Gaussian noise. Where do we get this type of noise? Normally the noise that is introduced in electronic circuit, and also the noise introduced because of the sensor variations, this will have usually Gaussian type of noise. So electronic circuit noise and sensor noise, and of course due to poor illumination and or high temperature, you can expect noise to be Gaussian. This is one type of noise. And you know the bell-shaped curve for Gaussian type of noise, and it is maximum at the mean value, and as you move away from the mean value it is decreasing. In fact, it's a symmetric curve, and depending on the deviation, you will know what is the maximum area that is covered by the distribution. For example, if you go from mu minus sigma to mu plus sigma, okay, it covers 70%. This is 70% of the total distribution. If you go from mu minus 2 sigma to mu plus 2 sigma, it is 95%. In fact, if you go from mu minus 3 sigma to mu plus 3 sigma, it almost covers 99 point some percentage. and at the origin the value will be 1 by root 2 pi sigma, that is also known. So when mu is 0, sorry, when z is equal to mu, this is 1, so it is 1 by root 2 pi sigma. Okay, so Gaussian distribution is one of the assumption that we do for noise. The second type of noise assumption we do is Rayleigh noise. This is the expression for PDF of Rayleigh noise. Again, here it has two parameters A and B. Okay, and this is the shape of Rayleigh noise. As you can see, it is slightly skewed to the right. Okay, and using this A and B, I can calculate the mean. These expressions it can be derived, but it is not required. What is important is the equation and also the shape and where it is normally occurring. So I can find the mean value and the variance by using these equations. So if I know A and B, I know the mean and variance of this noise, and it is usually a skewed distribution. That means to the right side you can see that it is more oriented. Normally there is an imaging called range imaging. Range imaging is usually used to find the distance of an object from the camera. So the distance is shown as an image. So that is range imaging. More about it, please have a look at literature. So in such type of imaging, this type of noise is more prominent. The third noise that we normally encounter is called Erlong noise or gamma noise, which is normally true in laser imaging. Okay. Again, more about laser imaging, please have a look. This is a distribution. Again, it has two parameters A and B, and this is also a skewed one, but if you carefully observe, the shape is slightly different. You can observe the shape of Rayleigh, the shape of gamma noise. Okay, and by using the parameters A and B, you can find the mean and variance. Exponential noise, all of you know exponential distribution, A into e power minus AZ. This is an exponential distribution. Again, in laser imaging, sometimes even exponential noise also could be there. And the mean and variance is given by these values. Uniform noise, usually it is not practical, this type of noise, but normally, for a random number generation, we usually use uniform distribution. This is only to just understand uniform distribution, and all of you know that it has a shape like this. This is uniform distribution. From A to B, the probability is constant. Okay, and again here mean and variance is depending on the parameters A and B. Okay, so this is about actually the various types of noise that normally encountered. The last one is called as an impulse noise. There is a spelling mistake here, please correct it. Since this is a PDF, I cannot correct. So salt and pepper type of noise, all of we have already seen this in previous chapter itself. It will have normally due to faulty switching while imaging, actually you get this type of noise, and all you know that either the pixel value will be very high or the pixel value will be very small. High value of pixel is an example for salt noise, and very low value of the pixel is an example for pepper noise. Okay, so ideally salt noise can be 255 and pepper noise can be 0, and this is the distribution curve. Simple. So it takes only two values A and B, and with the corresponding probabilities. Okay, so all of them put together, you can just have a look at the shape. This is the Gaussian distribution, Rayleigh, gamma, exponential, uniform, and impulse noise. which is salt and pepper type of noise. Okay, so next class we would be probably covering this. I'll be actually stopping at this stage. What I want you to think of is, I'll just explain this figure and I want an answer in the next class. This figure, all these gray values in the circular region, they are same. If you want, you can assume it to be some number. All these gray level values are same, and all these gray level values are same. This is an image. This is a synthetic image. We call it as a test pattern to explain something about how noise can be estimated. Now, what I want from you in the next class is, what will be the histogram of this type of image? I repeat, all these values are same, all these values are same, and all these values are same. So just think of it, when I have this type of image and plot its histogram, how does the histogram looks? Okay, so with this let us just stop.